I'm Dr. Samuel Alexander, mathematician and philosopher, and I'm going to be reading Numerical Stability and Gaussian Elimination by John Urschel, published in 2025 in the Notices of the AMS. In some sense, numerical analysis is a very old field. Well, arguably the oldest field in mathematics, you could say. It involves the study of algorithms for problems in continuous mathematics, and algorithms have been around at least since the Babylonians wrote them on tablets more than 4,000 years ago. But with the advent of the computer age in the 1940s, which made numerical calculations on a scale that was previously unimaginable not only possible but easy, understanding the stability of these algorithms became increasingly urgent. What kind of errors could creep in? What were the relative costs of accuracy and speed? John von Neumann and Hermann Goldstein, two of the architects of the modern computer, saw the need for numerical analysis instantly. At the Institute for Advanced Study, they developed the IAS machine, one of the first stored programmed digital computers, and sought to understand the effect of rounding and computations on it. In their seminal 1947 paper, Numerical Inverting of Matrices of High Order, von Neumann and Goldstein studied the stability of one of the oldest and most fundamental known algorithms, Gaussian elimination. Goldstein later wrote, "Indeed, von Neumann and I chose this topic for the very first modern paper on numerical analysis ever written, precisely because we viewed the topic as being absolutely basic to numerical mathematicians, as indeed it is. Gaussian elimination is very simple, so simple that the elimination method is taught to grade school students to solve systems of 2 or 3 equations. It is a straightforward way of solving n linear equations in n unknowns. The earliest variant appears in the 8th chapter of the ancient Chinese text, the 9 chapters on the mathematical art. And yet, despite being more than 2,000 years old and the most popular method for solving linear systems, some aspects of Gaussian elimination are still not understood. Goldstein and von Neumann took on the question of round-off error analysis for matrix factorization and inversion methods in part because of disagreements about the precision of the technique in certain cases. Alan Turing also presented an analysis around the same time. Figure 1. John von Neumann and the director of the Institute for Advanced Study, Robert Oppenheimer, in front of the IAS machine. Many mathematicians, including von Neumann himself, were quite pessimistic about the stability of the algorithm. Von Neumann famously changed his opinion over a year later and, together with Goldstein, provided the first framework for understanding it. However, their concrete results were limited, proving stability only in the special case of a symmetric positive definite matrix using complete pivoting. Despite the urgency of pinpointing and avoiding cascading rounding errors as computers became widely available, questions regarding the stability of Gaussian elimination remained. In many ways, it's Wilkinson who is the hero of this story, as it was not until his 1961 paper Error Analysis of Direct Methods of Matrix Inversion that a more complete analysis of the backward error in Gaussian elimination due to rounding errors was conducted. Most of the open questions that remain involve mathematically quantifying what Wilkinson, even in the 1960s, felt ought to be true. Figure 2. The earliest variant of Gaussian elimination appears in the 8th chapter of the ancient Chinese text, the 9 chapters on the mathematical art. The above procedure is presented to solve the following, which I'm not going to read. However, before we delve much further into the topic, allow me to remind the reader what exactly Gaussian elimination is. What is Gaussian elimination? Given an invertible matrix A and compatible vector B, Gaussian elimination is an algorithm to solve the linear system AX equals B for x in 2 stages. 1. Factor A into the product A equals LU of a lower unitriangular matrix L and an upper triangular matrix U, LU factorization. 2. Solve the linear systems Ly equals B for y, forward substitution, and Ux equals y for x, backward substitution. The second stage is straightforward and numerically stable, conditional on the stability of the first, and so we can devote our attention to the LU factorization. The algorithmic procedure for computing this factorization can be concretely summarized by the block formula A equals 2 by 2 matrix alpha y transpose x b equals 2 by 2 matrix 1 0 x over alpha I times 2 by 2 block matrix alpha y transpose 0 b minus x y transpose over alpha, where alpha is a scalar called the pivot, x, y are vectors, and b is a matrix. If b minus x, y transpose over alpha equals L1 U1 for a lower unitriangular L1 and upper triangular U1, then the LU factorization of A is given by A equals 2 by 2 block matrix A y transpose x b equals 2 by 2 block matrix 1 0 x over alpha L1 times 2 by 2 block matrix alpha y transpose 0 U1. This iterative procedure of rank 1 updates is essentially what a computer does when performing Gaussian elimination, up to one crucial detail: what to do when the pivot alpha equals 0. In this case, some perturbation of the rows and or columns of A are needed to put a non-zero entry in the pivot's place. In reality, a pivot equaling 0 is not the only difficulty computers contend with. Very small pivots can be just as dangerous, and the prospect of errors compounding rapidly can also lead to wildly incorrect results. Some pivoting strategy is required to avoid these situations, a topic we'll leave here for later. It's worth noting that Gaussian elimination has a number of equivalent mathematical representations, each of which can prove useful in analysis. For example, the block submatrices iteratively created during this algorithm can be tied to the original matrix through a Schur complement, i.e., Gaussian elimination can be equivalently represented by a sequence of k by k matrices A super k for k equals n to 1, satisfying A super n equals A and A super k equals zk minus yk wk inverse xk, where A equals the 2 by 2 block matrix wk xk yk zk. In this representation, the resulting LU factorization of A is encoded in the first row and column of each of the iterates A super k. This procedure can also be represented entirely through the language of determinants. Because the determinant of a triangular matrix is the product of its diagonal entries, each entry of L and U is equal to a ratio of minors, determinants of submatrices of A. The right representation of the algorithm largely depends on the specific property such setting being studied. Gaussian elimination is quite an amazing algorithm. It's not only the oldest in linear algebra, but it is also still the most popular method for numerically solving an unstructured linear system. And it has the benefit of being one of the few linear algebra algorithms that works over an arbitrary field. The QR factorization, for instance, requires the notion of an inner product. Here in this article, I'd like to focus on this algorithm through the lens of computation, in particular, its numerical stability, and journey through both the mathematical discoveries that have occurred and the questions that remain since the early work of von Neumann, Wilkinson, and others over 60 years ago. However, to do so, we first need to take a detour into the fundamentals of numerical computation. Floating point arithmetic. To the untrained eye, at this point a natural question may arise. Why discuss error at all when the Gaussian elimination algorithm is exact? While the LU factorization of a rational matrix is indeed rational, the lengths of the matrix elements may be prohibitively long for fast computation in practice. As an example, consider solving a 1000 by 1000 linear system with random binary coefficients in the Julia programming language. N equals 1000, A equals rand bool n, B equals rand bool n. First we solve AX equals B by using 64 bits per number, time x hat equals float64.a backslash float64.b. I don't know Julia, so I don't know how to pronounce these symbols. 0.01 seconds. Next, we solve ax equals b exactly without any rounding. Time x equals rational big int dot a backslash rational big int dot b, 2,389.89 seconds. And output the error from our first computation, norm of x minus x hat, quantity divided by norm of x, 4.34 e to the minus 13. The first computation took only 10 milliseconds and gave an answer accurate to about 10 to the minus 13, while the second took nearly 40 minutes. This is due to the growing complexity of the numbers encountered. For instance, the numerator and denominator of the first entry of x are both over 3200 bits long. For this reason, in practice, numbers are only approximately stored using what is called a floating point number system, blackboard bold F, essentially an adaptation of scientific notation tailored for computers with precision constraints. This system is parameterized by four numbers beta, t in the naturals, e min, e max in the integers, and consists of all numbers of the form floating points equals plus or minus m times beta to the e minus t, such as m, e are integers, 0 less than or equal to m less than or equal to beta to the e minus 1, e in the closed interval from e min to e max. See figure 3 for an example of the bit string representation of 0.15625 in IEEE single precision, and figure 4 for visual representation of the elements of the floating points for a toy model with beta equals 2, t equals 3, e min equals minus 1, and e max equals 3. Let's see, figure 3, the bit string for 0.15625 equals 1/8 plus 1/3 over 32 in single precision, 32 bits. The number is represented as 1 plus 1/4 quantity times 2 to the minus 3. Not 1 plus 1/4 equals 1.01 in base 2. The exponent bias is 127, so the stored exponent is 0.1111100 and binary equals 124. Figure 4, the non-negative floating point numbers in a toy model with beta equals 2, t equals 3, and e in the closed interval from minus 1 to 3, which appears in Nick Higham's What Is series. When a number x in the reals is input, it is stored as float of x in the floating points, where float, reals to floating points, rounds real numbers to the nearest element in the floating points. The effects of rounding when inputting numbers or performing computations can be effectively bounded based on the unit round-off bold U equals beta to the 1 minus t, the distance between one and the next element of the floats. In particular, ignoring issues of overflow and underflow, for any x in the reals, float of x equals x times 1 plus delta for some abs delta less than or equal to bold U. An analogous property also holds for fundamental computer operations given x, y floating points and a standard operation op, such as plus, minus, times, or division. Float of x op y equals x op y quantity times 1 plus delta for some abs delta less than or equal to bold U. This property is sometimes referred to as the fundamental axiom of floating point arithmetic. Numerical stability and an elegant mathematical problem. Suppose someone wanted to approximate a function f at a point x using an algorithm f hat. How should they judge how well they did? One measure would simply be the distance between the exact and computed solutions, abs f of x minus f hat of x, called forward error. However, if the derivative of f was very large, then this might not be the most fair measure of good algorithm, as a small change to the input data x could drastically change the output f of x. Instead of asking whether the computed solution is almost the right answer, we could consider whether it is the right answer to almost the right question, i.e., does there exist an x hat such that f hat of x equals f of x hat and abs x minus x hat is small? This is called backward error, and though this measure is also imperfect, in this language we can quickly measure the stability of Gaussian elimination. Thinking of an LU factorization as a function from a to the power L and u, i.e. f of a equals the power LU, this procedure is backward stable if the computed LU factorization f hat of a equals L hat u hat satisfies L hat u hat equals a plus h for some h that's not too big. Let abs a denote the matrix with the absolute values of the entries, i.e. the abs value of aij equals the abs value, i.e. the ij entry of abs a equals absolute value of the ij entry of a, and consider the matrix inequality a less than or equal to b component-wise. Some version of the following theorem appears in many numerical analysis texts. Theorem: let a in float to the n by n. If no zero pivots are encountered during Gaussian elimination, then the computed lower and upper triangular matrices L hat U hat in floats to the n cross n satisfy L hat U hat equals a plus h, where abs h less than or equal to 2 times n minus 1 quantity times bold U times abs a plus abs L hat times abs U hat all plus big O of bold U squared. While I won't reproduce the proof, I'd like to give some intuition about how these types of results can be proven. One idea is to proceed by induction and consider a single step of Gaussian elimination from A equals 2 by 2 block matrix alpha y transpose xb to 2 by 2 block matrix alpha y transpose 0b minus xy transpose over alpha. In floating point arithmetic, this procedure, float of b minus float of x over alpha times y transpose, involves 3 steps, and therefore introduces 3 errors of relative sizes at most bold U. Assuming that the theorem statement holds for matrices of dimension n minus 1, i.e. the computed L1 hat and U1 hat for float of b minus float of x over alpha quantity y transpose, and also satisfies the statement, the result follows pretty quickly as L hat equals 2 by 2 matrix 2 by 2 block matrix 1 0 float x over alpha L1 hat, and U hat equals 2 by 2 block matrix alpha y transpose 0 U1 hat. The big takeaway from theorem 1 is that the stability of Gaussian elimination in floating point arithmetic can be estimated by a single mathematical quantity, the largest entry in L hat or U hat, scaled by a. It is such a central quantity that we give it a name, the growth factor. G of a, growth of a, equals maximum magnitude entry of L, or maximum magnitude entry of U over maximum magnitude entry of a. And they're writing this maximum magnitude using double vertical bars sub max. Theorem 1 converts the practical question of the stability of this algorithm in computation to a purely mathematical one regarding the size of entries of L and U relative to A. The game, so to speak, is to choose a strategy for permuting rows and columns of A, say with permutation matrices PQ, so that 1. The strategy can be implemented quickly, and 2. The resulting factorization PAQ equals LU has a small growth factor, growth of PAQ. The modern story. Though von Neumann and Goldstein may have been the first to present a more encouraging perspective regarding Gaussian elimination, it wasn't until Wilkinson came along that a more robust understanding of the computational stability of this algorithm emerged. For instance, a variant of Theorem 1 and the resulting observation that the growth factor, growth of A, can be used to estimate stability were first realized by Wilkinson. Wilkinson's early work on the subject included the analysis of Gaussian elimination primarily under 2 popular pivoting strategies. 1. Complete pivoting, permuting rows and columns so that the pivot is always the largest entry in the matrix, i.e. abs a11 super k equals the max magnitude entry of a super k, k equals 1 through n. And 2, partial pivoting, permuting rows so that the pivot is always the largest entry in the first column, i.e. absolute value of a11 super k equals the infinity norm of the vector a colon 1 super k, k equals 1 through n. These two pivoting strategies are quite different, a fact reflected by the nature of the questions regarding them. Complete pivoting, famously referred to by von Neumann as customary, then called positioning for size, is a popular theoretical technique with reasonably good guarantees on stability that today is primarily used when high accuracy is desired. Partial pivoting, on the other hand, is a more interesting situation. The need to compare far fewer entries of each iterate a super k means that partial pivoting is much faster than complete pivoting and adds little to the overall runtime of the Gaussian elimination algorithm. However, the issue here is that this procedure is known to be horribly unstable in the worst case, see below. Still, Gaussian elimination with partial pivoting remains the most popular method for solving an unstructured linear system numerically. The / command in MATLAB and Julia and the linalg.solve command in Python all employ this method by calling LAPACK routines when faced with an arbitrary matrix. Its use, in spite of this worst-case instability, can be concisely explained as follows. It is simply faster, in a practical sense, than any other known algorithm, and historically, numerical analysts have believed that the situations where it is unstable are extremely rare. For instance, the QR factorization, where A is written as the product of an orthogonal matrix Q and upper triangular matrix R, is probably the most popular alternative to Gaussian elimination. This approach solves a linear system Ax equals B by computing A equals QR and applying backward substitution to Rx equals Q transpose B. This factorization is mathematically equivalent to applying Gram-Schmidt orthogonalization to the columns of A, though, especially when Q does not need to be formed explicitly, in practice, it is often computed by applying simple orthogonal transformations to A to convert it to an upper triangular matrix R. While the QR factorization computed by, say, householder reflections is incredibly stable, it requires roughly 4/3 n-cubed operations to compute, with Q only implicitly computed. While a simple counting argument applied to equation 1 implies the LU factorization only requires roughly some k equals 1 to n2 k squared at approximately 2/3 n-cubed operations, k squared for the vector outer product, k squared for subtraction, half the cost compared to QR. While an exact comparison of computational efficiency is far more complicated than simple operation counting, often involving the movement of data in the computer's memory system, the main takeaway is that Gaussian elimination paired with partial pivoting remains the fastest way to compute the solution to an unstructured linear system. In some sense, the use of Gaussian elimination is a trade between guaranteed stability for a factor of 2 in runtime. In what remains of this article, I'd like to talk a little about complete pivoting and partial pivoting. In each case, starting with the early contributions of Wilkinson and discussing the modern developments while briefly providing some mathematical insight into the types of techniques involved. It's worth noting that many results do not fall under either complete or partial pivoting, my favorite two being the lower bounds of Higham and Higham for the growth factor of a matrix under any pivoting strategy, and the estimates of Demel, Grigori, and Rusciano on the expected log growth of a matrix pre and post multiplied by random orthogonal matrices. I encourage the motivated reader to seek the results out, as well as many other research directions I was unable to mention here due to space constraints. For more details about the complete and partial pivoting, Higham's accuracy and stability of numerical algorithms for complete pivoting, and Chafethan and Bau's numerical linear algebra for partial pivoting are good starting points. The theory of complete pivoting. In 1961, Wilkinson produced the following bound for a completely pivoted matrix A in general linear of complex field. Growth of A less than or equal to radical n times 2 times 3 to the 1/2 times ... times n to the 1 over n minus 1, all quantity to the 1/2, less than or equal to 2n to the power 1/4 natural log n plus a half. The proof is incredibly short, requiring 1 page of mathematics and using only Hadamard's inequality applied to the matrix iterates A super k in complex field to the k cross k. However, the proof is also somewhat mysterious. I'd like to sketch a slightly more transparent proof through the language of linear programming. Let pk equals the max argument of matrix A sub k. Recall that under complete pivoting, this is the magnitude of the pivot of A super k. Hadamard's inequality, that the modulus of the determinant of a matrix is at most the product of the two norm of its columns applied to A super k, implies that product I equals 1 to kpi equals the determinant of A super k less than or equal to k to the k over 2 times the max argument of A super k, max argument being raised to the kth power, equals k to the k over 2 times pk to the k. The leftmost equality is the result of L having 1s and U having the pivots on their respective diagonals. The maximum kth pivot viewed as a function of k is non-decreasing, and so the maximum value of p1 over pn under these constraints provides an upper bound for the maximum growth factor. The transformation qk equals natural log pk produces the linear program max q1 minus qn such that sum I equals 1 to k qi less than or equal to k over 2 natural log k plus k qk for k equals 1 through n. We can rewrite this in matrix vector form as max c transpose x such that ax less than or equal to b, where x equals the transpose of q1 dot dot qn, c equals the transpose of 1 0 dot dot 0 minus 1, and ax less than or equal to b is given by matrix minus 1 minus 1 minus 2 dot dot minus n minus 1 on the diagonal, and all 1s under the diagonal, and all 0s above the diagonal, times vector q1 q2 dot dot qn less than or equal to vector 0 2 over 2 log 2 3 halves log 3 dot dot n over 2 log n, and holds entry-wise. The matrix A has an easily computable inverse with aij inverse equals minus 1 for I bigger than or equal to j equals 1, aij inverse equals minus 1 over I minus 1 for I equals j bigger than 1, aij inverse equals minus 1 over j times j minus 1 for I bigger than j bigger than 1. The quantity A inverse transpose times C, there's a verb missing here. He writes the matrix with diagonal minus 1, minus 1, minus a half, dot, 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 minus 1 over n minus 1, and then minus 1, dot, 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 minus 1 in the top row, minus 1 half, dot, 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 minus 1 half in the second row, dot, 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 minus 1 over n minus 2 times n minus 1 in the penultimate row, zeros under the diagonal, all times the vector 1, 0, dot, 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 0, minus 1, equals the vector 0, 1 half, dot, 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 1 over n minus 2 times n minus 1, 1 over n minus 1, is entry-wise non-negative, implying inequality 3. q1 minus qn equals the transpose of A inverse C, all times ax, less than or equal to the transpose of A inverse C, all times b, equals 1 half of natural log n plus some k equals 2 to n natural log k over k minus 1. Wilkinson felt that this bound was extremely pessimistic, a viewpoint shared by most numerical analysts today. In the same paper, he remarked that in our experience, the last pivot has fallen far below the given bound, and no matrix has been encountered in practice for which p1 over pn was as large as 8. This sentiment was soon quantified, and a folklore conjecture was formed that the growth factor under complete pivoting of a real n by n matrix was most n. A great deal of research went into proving this conjecture for small n. The exact conjecture proved to be false, illustrated by a 13 by 13 matrix with growth factor 13.02 found numerically by Nick Gold in 1991 and verified in exact arithmetic by Alan Edelman a year later. But still, the larger question of how this quantity behaves remains. Question 2. What is the asymptotic behavior of the maximum growth factor under complete pivoting? One theoretical consequence of this question is that if the growth factor is bounded by a polynomial in n, then only big O of log n bits are required to perform Gaussian elimination accurately. This question is one that my collaborators and I have made some progress on recently, producing a lower bound of 1.0045 n for all n bigger than or equal to 11, and an upper bound of n to the power 0.20781 natural log n plus 0.91. Wow, you can tell you're reading a numerical analysis paper here. The former is the first disproof of the 1960s folklore conjecture for all n larger than a constant. The latter is the first improvement to Wilkinson's 1961 bound and involves finding further constraints on the pivots of A and solving a much more complicated linear program. However, the gap between the upper and lower bounds for this quantity still remains quite large. Partial pivoting and a practical problem. In contrast, for partial pivoting, where the rows of A are permuted so that abs A11 sub k bigger than or equal to abs AI1 sub k for all I and k, the worst-case behavior is incredibly well understood. Because the pivot A11 sub k is the largest entry in the first column, the largest entry of A sub k minus 1 is at most twice that of A sub k, leading to an upper bound of 2 to the n minus 1 for the growth factor of an n by n matrix under partial pivoting. In his 1965 text, The Algebraic Eigenvalue Problem, Wilkinson showed that this bound can be obtained, illustrated by the example matrix A equals a certain matrix. It looks like it's all ones on the diagonal, all ones in the rightmost column, all zeros above the diagonal except for that rightmost column, and all minus ones below the diagonal. After one step of Gaussian elimination, the resulting matrix looks nearly identical in structure to the original, except the last column has doubled in size, changing from a column of ones to a column of twos. A2 colon n comma 2 colon n minus bold 1 quantity e vec superscript big T subscript n minus 1, where 1 bold equals transpose of 1 dot 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 1. This doubling occurs at every step, resulting in the last entry of u equaling 2 to the n minus 1. This exponentially large growth factor can lead to catastrophic errors even for well-conditioned matrices. To see this in practice, let's consider the solution to a 100 by 100 linear system Ax equals b, where A is the example matrix in equation 4. X is a Gaussian vector, and of course, b equals a times x. This setup allows us to explicitly compute the numerical error, as we already know x exactly. Using the Julia programming language, we first define the Wilkinson matrix from equation 4. Wilk of n equals... I'm not going to read this. I don't know Julia, so I don't know how any of these symbols are read. Next, we initialize a randomly, select x, and compute b equals ax. Solving for x numerically using the built-in backslash command, which employs Gaussian elimination with partial pivoting, we're in for quite a surprise. Norm of x minus a backslash b quantity over norm of x is 1.86233, etc. The computed solution, typically accurate to about 10 to the minus 13, has relative error greater than 1, e.g. 0 is a better guess. To really stress the inaccuracy of the computed solution, we can take a look at the last 10 digits of x and our computed a backslash b. This is not caused by the condition number. The condition number of a is 44.802. I don't have any idea what that means, as linear condition numbers are quite acceptable for most applied problems. No warning or error message is given. The same phenomenon occurs in the majority of programming languages, e.g. backslash in MATLAB, lineage.solve in Python, etc. Many researchers suspect that the situations where partial pivoting fails are rare. In matrix computations, Golub and Van Loon state that although there is still more to understand about rho, the growth factor, the consensus is that serious element growth in Gaussian elimination with partial pivoting is extremely rare. The method can be used with confidence. Of course, even rare instances become important to understand as the number and variety of computations increases exponentially. For partial pivoting, the majority of modern research is devoted to either quantifying how rare this worst-case behavior is, or illustrating how this worst-case behavior can be avoided altogether. In 2012, Nick Chafethan, the then president of SIAM, described two of the biggest unsolved problems in numerical analysis. The first, unsurprisingly, was fast matrix multiplication. The second was, why does Gaussian elimination work? Inspired by experiments, he conjectured that the growth factor of a Gaussian matrix under partial pivoting scales like radical n and offered $1,000 for a proof. Conjecture. Let A be an n by n Gaussian matrix, i.e. Aij is independent and identically distributed n of 0, 1. Then, for any alpha m bigger than 0, the probability that the growth factor of A under partial pivoting is larger than n to the 1/2 plus alpha is at most n to the minus m for all n sufficiently large. While some asymptotic properties require large values of n to emerge, here the radical n behavior of the growth factor is abundantly clear even for small values of n. However, proving this exactly seems difficult for reasons we will soon discuss. Figure 6. Histograms of 100,000 samples of the growth factor under partial pivoting divided by radical n of rand n of n for n equals 2 to the k equals 8 through 11. The largest growth factor encountered here was less than 2 radical n. Another approach for analyzing partial pivoting is through smoothed analysis, a technique popularized by Spielman and Teng that strikes a balance between average case and worst case analysis. A smoothed analysis of an algorithm is a study of its performance for a mild random perturbation of an arbitrary input. For example, even though Wilkinson's matrix is a highly unstable instance, upon mild perturbation, even without pivoting, the growth factor decreases significantly. In some sense, smoothed analysis is a generalization of average case analysis with the added benefit of being not only descriptive but prescriptive. In particular, rather than speculate about the rarity of unstable instances in practice, smoothed analysis offers a concrete solution to avoid these instances altogether in a true probabilistic sense through the introduction of a modest amount of noise. In 2006, Sankar, Spielman, and Teng provided a smoothed analysis of Gaussian elimination without pivoting. Here's one sample result. For an arbitrary n by n matrix A with the true norm of A less than or equal to 1 and an n by n Gaussian matrix B, the LU factorization LU equals A plus epsilon B, epsilon less than or equal to 1 satisfies the probability that the infinity norm of u divided by the infinity norm of A plus epsilon B is bigger than 1 plus t is less than 1 over radical 2 pi times n plus 1 quantity over t epsilon. I'd like to give some intuition about how a result like this, or say one about a Gaussian matrix, is often proven. By equation 2, the entries of U are elements of a Schur complement involving the leading submatrices of A, and the only way the elements of U can become much larger than those of A is if a leading submatrix of A has a very small singular value. In practice, growth factor estimates for these types of problems essentially reduce to singular value type estimates, or similarly bounding the application of the inverse of a leading submatrix to a given vector. For example, inequality 5 essentially relies on the following property of a random Gaussian distribution, lemma. let A in reals to the n times n and B be a Gaussian matrix, then for any fixed unit vector x in reals to the n, the probability that the 2 norm of a plus epsilon b quantity inverse x is bigger than t is less than radical 2 over pi times 1 over t epsilon. While I won't provide a proof of this, I can give the basic idea in a few lines. Because Gaussian matrices are distributionally invariant under orthogonal transformations, we can assume x equals the transpose of 1, 0, 0, 0, dot, 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 0, and simply bound the size of the first column of the inverse of a plus epsilon b. The size of this column is exactly the inverse of the inner product between the first row of a plus epsilon b and a unit vector from the orthogonal complement of the remaining n minus 1 rows, reducing the problem to one involving the inner product between a fixed unit vector and a Gaussian one, which is well studied. Overall, the average case in smoothed analysis without a pivoting is fairly well understood. However, making analogous statements for partial pivoting has proven much more difficult. Partial pivoting can be viewed as a greedy determinant maximization where the kth row is chosen to maximize the leading k by k minor. Intuitively, this reordering should significantly improve the situation as larger leading minors seem beneficial. This intuition is supported by practice, as partial pivoting is usually, though certainly not always, far superior to no pivoting. However, this greedy procedure makes mathematical analysis significantly more difficult, as it introduces dependence between elements of the random perturbation. For instance, Sankar, in his PhD thesis, performed a smoothed analysis of partial pivoting, but due to the mathematical complications introduced by pivoting, was only able to prove a quasi-polynomial bound for growth. Recently, Huang and Tikhomarov managed to prove that the growth factor under partial pivoting of Gaussian matrix is polynomial. One key idea was a quantification of how Gaussian the remaining n minus k rows of a Gaussian matrix are after k rows have already been chosen during a partial pivoting, e.g. understanding how much randomness persists in spite of the pivoting procedure. This result is still quite far from the expected Radcliffe behavior, and the arguments presented do not appear to directly translate to the smoothed analysis setting. There is still quite a gap between what we observe and what we can prove mathematically, though. The problems of producing a smoothed analysis of partial pivoting with a polynomial bound, or better yet one at least as strong as inequality 5 and proving Chephethan's $1,000 conjecture, both remain completely open. If you solve it, that'll be worth way more than $1,000. Acknowledgement: the author thanks Louisa Thomas and 2 anonymous referees for significantly improving the style of presentation. All experiments were performed in the Julia programming language on a Mac Studio with an Apple M2 Max chip and 32 gigabytes of unified memory. Figures 6 and 7 were created using the built-in LEU command in double and quadruple precision, respectively. Figure 7. A log-log plot of the growth of a plus epsilon b, the growth factor without pivoting, with respect to epsilon for a 100 by 100 Wilkinson matrix A, and a fixed Gaussian matrix B. Setting epsilon equals 10 to the minus 16, approximately the unit ground off bold U in double precision, already drops the growth from approximately 10 to the 30th to 10 to the 18th. That almost entirely went over my head, but interesting nevertheless. Please like, comment, and subscribe. Until next time.